Look around you. What do you see? Take a moment to really observe your surroundings. A chair, a table, perhaps a window to the world outside. These are all familiar objects, grounded in place. Now imagine for a moment that everything suddenly became weightless. Chaos would ensue as objects floated and we drifted aimlessly. This is where gravity comes in. Gravity is an invisible force that keeps our feet on the ground and prevents us from floating away. It's the force that makes an apple fall and the moon orbit the Earth. Gravity shapes our universe, governing the motion of planets, stars, and galaxies. Gravity is a force of attraction, pulling objects toward each other. It exists between any two objects with mass. The more massive an object, the stronger its gravitational pull. That's why we feel Earth's gravity more than a book's, even though the book also has its own gravitational pull. This difference in mass makes Earth's gravitational pull more noticeable. Gravity holds us to the Earth, keeps the moon in orbit, and dictates the dance of galaxies. It's a universal force. Think about throwing a ball into the air. It goes up, slows down, and falls back down. This is gravity at work, constantly pulling the ball back down. This invisible force shapes the motion of objects both big and small. Gravity is a constant companion, an ever-present force that shapes our world in countless ways. From walking to the dance of celestial bodies, gravity is the invisible hand that governs the universe. It's a force that connects us all. For centuries, the nature of gravity remained a mystery, an enigma that puzzled the greatest minds of the time. Then came Sir Isaac Newton, an extraordinary physicist and mathematician who in 1687 revolutionized our understanding of this fundamental force with his groundbreaking work. He proposed the law of universal gravitation, a simple yet profound explanation for how gravity works, which has stood the test of time. Newton's law states that every object in the universe attracts every other object with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This means that the more massive an object, the stronger its gravitational pull.
This might sound complicated, but it can be understood with a simple equation. F equals G times the product of m1 and m2 divided by r squared. This equation elegantly captures the essence of gravitational interaction. Where F is the force of gravity, G is the gravitational constant, m1 and m2 are the masses of the two objects, and r is the distance between their centers. Each of these components plays a crucial role in determining the gravitational force.
Let's break it down further to understand its implications. The equation tells us that the force of gravity increases when the masses of the objects increase. This is why larger celestial bodies like planets and stars have such strong gravitational fields. Imagine holding a tennis ball and then a bowling ball. The difference in weight is due to the difference in their masses. The bowling ball feels heavier because it has more mass and therefore a stronger gravitational pull towards the Earth. This is a direct demonstration of Newton's law in everyday life.
The equation also tells us that the force of gravity decreases as the distance between the objects increases. This inverse relationship is crucial in understanding the behavior of objects in space. Think about moving away from a magnet. The magnetic force weakens as you increase the distance. The farther you move, the weaker the magnetic force becomes. This analogy helps us grasp the concept of gravitational force diminishing with distance. Similarly, the farther apart two objects are, the weaker the gravitational force between them. This principle is fundamental in understanding the vast distances and interactions in our universe.
We've all heard the story of Newton and the apple, how the falling fruit sparked his ideas about gravity. This familiar force, the pull we feel towards the Earth, is called acceleration due to gravity, denoted by the letter G. It's the acceleration that objects experience because of Earth's gravitational pull. The value of G on Earth is approximately 9.8 meters per second squared. This means that if you drop an object, ignoring air resistance, its speed will increase by 9.8 meters per second every second it falls.
However, G is not constant everywhere on Earth. It varies slightly depending on factors like altitude and the local density of the Earth. If you were to climb a mountain, you'd be slightly farther from the Earth's center and therefore experience a slightly lower G. Conversely, if you were to go deep into a mine, you'd be closer to the Earth's center and experience a slightly higher G. These variations are small but measurable and demonstrate that even Earth's gravity is not uniform.
The acceleration due to gravity is a fundamental concept that helps us understand how objects move near the Earth's surface. It's a testament to the invisible force that keeps us grounded and shapes our everyday experiences. In the early 17th century, Johannes Kepler, a brilliant astronomer, formulated 3 laws that describe the motion of planets around the Sun. His work was revolutionary and changed the way we understand our solar system. These laws, known as Kepler's laws of planetary motion, provided a groundbreaking understanding of celestial mechanics. They were a significant departure from the ideas that had dominated astronomy for centuries. Kepler's first law states that planets move in elliptical orbits with the Sun at one focus. This was a major shift from the previously accepted notion of circular orbits. This was a radical departure from the circular orbits proposed by earlier models. Kepler's insight helped to explain the observed planetary motions more accurately.
Kepler's second law, often called the law of equal areas, tells us that a line connecting a planet to the Sun sweeps out equal areas in equal times. This law explains the varying speeds at which planets travel in their orbits. This means that planets move faster when they are closer to the Sun and slower when they are farther away. This variation in speed was a key observation that Kepler made. Kepler's third law establishes a relationship between the time it takes for a planet to orbit the Sun and its average distance from the Sun. This law provided a mathematical framework for understanding the motion of planets. Specifically, the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. This relationship is fundamental to the study of orbital mechanics.
Kepler's laws not only describe planetary motion with remarkable accuracy, but they also provided a new way to look at the universe, but also laid the groundwork for Newton's theory of gravitation. Newton built upon Kepler's work to develop his own laws of motion and universal gravitation. They showed that the motion of celestial bodies could be predicted and understood through mathematical principles. This predictability was a major advancement in the field of astronomy. These laws continue to be a cornerstone of modern astronomy, helping us to explore and understand the vast complexities of our universe. They remain essential tools for astronomers and scientists today.
Gravitational potential energy, it's the energy an object possesses due to its position in a gravitational field.
Exactly. The higher an object is, the more gravitational potential energy it has.
And, when we talk about escape velocity, we're referring to the speed an object needs to break free from a planet's gravitational pull.
Right, for Earth that speed is about 11 kilometers per second.
That's why rockets need so much power to leave our atmosphere. They have to overcome Earth's gravitational pull.
Once in space, a satellite needs to achieve the right orbital velocity to stay in orbit.
Orbital velocity is the speed a satellite needs to balance gravitational pull and its inertia. This determines its time period, or how long it takes to complete one orbit.
The energy of a satellite in orbit is a combination of its kinetic and potential energy.
Absolutely. Without understanding gravitational potential energy, escape velocity, and orbital mechanics, sending satellites or astronauts into space would be impossible.
All right, let's dive into the fascinating world of satellite motion.
Satellites orbit the Earth due to the perfect balance between their velocity and the gravitational pull from our planet.
Exactly. This delicate dance ensures that satellites stay in orbit, providing us with crucial data and communication services.
And it's quite amazing how these man-made objects follow the same principles that govern the motion of planets and moons.
Now let's explore some practical applications of gravitational concepts.
Gravity isn't just a theoretical concept. It has real-world applications, like in engineering and construction.
Absolutely. Engineers use gravitational principles to design stable structures and ensure safety in various projects.
And don't forget about the role of gravity in space exploration, guiding spacecraft and satellites on their missions.
Gravity is the invisible force that binds our universe together. From the smallest particles to the largest galaxies, gravity governs the motion and interaction of all matter. It shapes the cosmos, creating stars, planets, and even black holes. Without gravity, the universe as we know it simply wouldn't exist. Let's review some key terms we've covered. Gravitational force, the attractive force between two masses. Orbit, the curved path of an object around a point in space. Satellite, an object that orbits a planet or star. Kepler's laws, 3 laws describing the motion of planets around the sun. Escape velocity, the minimum velocity needed to break free from a celestial body's gravitational pull.